quantum field theory applies standard quantum mechanics to fields. All right, it's an application of the rules of quantum mechanics as you know them. So a system has a state psi that evolves in time according to the Schrödinger equation. This is in the Schrödinger picture as I've written it. Time evolving vector in Hilbert space. If you know the Hamiltonian of the system, you can calculate the time evolution of the quantum state. There's no such thing as relativistic quantum mechanics. What you're really doing in quantum field theory, you're applying the quantum mechanics that you've applied to low energy systems, you're applying them to fields, and the kind of fields in nature include, so the electromagnetic field, which classically obeys Maxwell's equations. It also, the fields in nature also include the Dirac field, which classically, I'll put classically in brackets. In classical physics you don't really need the Dirac field. But formally speaking, what we do in quantum field theory, we imagine that there is this classical field which obeys the Dirac equation, and we quantize it according to the usual rules. There's also the scalar field, the Higgs field, usually described in terms of a scalar field. It was discovered recently. So classically, it obeys the Klein-Gordon equation. All right, so so these systems, what you do is you write down these classical systems. Normally, you would, instead of writing down just the wave equation, you derive them from a Lagrangian, and you find the corresponding Hamiltonian, and that Hamiltonian is what we put in here. So these classical systems, so classical fields, must be quantized. So what does this mean? It means so the classical electric and magnetic fields become operators, or you're working in terms of the vector potential, which is what we're going to do, what you normally do in quantum theory. It becomes an operator field. The Dirac field, which we met briefly last time, is a four-component complex field. It becomes a four-component operator. The scalar field also, of course, becomes an operator field. Now, what you need to know is to quantize, we need to know the Hamiltonian. Now, later on in the course, we're going to do a formal theory derive, let us say you've got some field equation, maybe the Klein-Gordon equation or Maxwell's equation. You derive the field equations from a Lagrangian. Actually, it's going to be a Lagrangian density. In field theory, there's something, I mean, the Lagrangian that you're familiar with is just the integral of, so the Lagrangian you're familiar with is an integral over space of a Lagrangian density. There's something called a Lagrangian density. And once you've figured out the Lagrangian that gives you your field equations, from the Lagrangian or the Lagrangian density, you can find the Hamiltonian H. Okay, and of course here, sorry, I should have mentioned that when you quantize the fields, also the Hamiltonian becomes an operator. All right, and we're going to find the Hamiltonian from the Lagrangian. We're going to do that later on, but you don't need to worry about that now. Okay, so one other thing we said is that in quantum field theory, it's convenient to use the Heisenberg picture. Convenient to use the Heisenberg picture so where the state psi is static and operators evolve according to instead of the Schrödinger equation, you have the Heisenberg equation of motion, and so eigenvectors, if you're looking at eigenvectors of the operator, they evolve. Really, we have, you could write it like this, that the eigenvectors evolve and the state stays fixed. Now, this is convenient. Why is it convenient? Because the operator field equations take the same form as the classical field equations, whose well-known properties, the classical field equations have well-known properties we can exploit. We can exploit those properties. So basically we're looking at a theory with operator fields, but if the equations that the field satisfy are the same as the classical field equations, well, there's already a lot you know about properties of the classical field equations. So you can use those properties, and they're going to be very useful. Okay, now something came up. Someone sent me an email. Just want to clarify a widespread confusion about the Heisenberg picture. Let me maybe do it here. Just want to clarify this because it does come up a lot, and I forgot to mention it last time. So we were saying that, well, I can have, here is your state. In the Schrödinger picture, psi is evolving with time, and the states, the eigenvectors are fixed, the operators are fixed, so the eigenvectors are fixed. In the Heisenberg picture, the state vector is fixed, but the eigenvectors evolve. In fact, you could write it like this. We wrote this down last time. They just evolve like this, and so of course omega evolves. Now what you're doing is, in the Schrödinger picture, the state vector is evolving like this, and these are fixed. In the Heisenberg picture, the state is fixed, and the eigenvectors are rotating in the opposite sense. Now the point is that inner products like this are the same in both pictures. Okay, if I write in the Schrödinger picture, if I write this is exactly the same as this thing. All right, and we discussed that. But now, so what is it I didn't discuss? The point I didn't discuss is about what you normally call the wave function. If I have, say, one particle wave function, let's write this, one particle wave function, which is the inner product of, normally it's the inner product of a position state with the Schrödinger, with the state vector. This is how you would write it in the Schrödinger picture. In the Heisenberg picture, you have time-dependent position operators and time-dependent position eigenstates and a static state vector. Okay? And these are the same. These are the same. You get the same way, just as you get any inner product is the same in both pictures. This inner product of the state with a position eigenstate is also the same in both pictures and is equal to the wave function. And the wave function, of course, satisfies the Schrödinger wave equation. I decided t, writing it in terms of wave functions. Now here's where the confusion, there's a common confusion, is that, let me write it explicitly here, the wave function psi xt and its wave equation. So it's what you might call, what you often call the position space wave function. And its wave equation, let's write it out explicitly for one particle, is the same in both pictures. Some books, or some people, sometimes it is implied that these are particular to the Schrödinger picture. To the Schrödinger picture. No. Okay, the position space wave function and the position space Schrödinger equation is the same in both pictures. Okay, these amplitudes like this, these inner products, are the same in both pictures. You might think, hey, the way people phrase this, so what you need to do is you need to distinguish. Here's where the confusion is. You must distinguish the Schrödinger wave equation which is the same in both pictures. You have to distinguish that the Schrödinger equation in Hilbert space which is I decided t equals h psi, which is particular to the Schrödinger picture. Okay, so I hope that maybe I'm labeling this, maybe it's obvious to you, but my impression, a lot of books, a lot of people, they hang on, the way it's written or presented, it somehow gives you the impression that this has got something to do with the Schrödinger picture. No, 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 no. You have to distinguish. The Schrödinger wave equation for position space wave function is the same in both pictures. The abstract Schrödinger equation in Hilbert space, where you have a state vector that's evolving in time, that's particular to the Schrödinger picture. In the Heisenberg picture, this is not true. This vector, state vector is static and the operators evolve. But in either picture, if you actually look at the amplitudes, the inner products of the state and position state, you get this complex amplitude psi, and that's always the same in both pictures. So I hope I haven't caused maybe more unnecessary confusion. Or anyway, are there any questions about that, just in case? Is that clear? That's clear. Okay, maybe I just wasted my time. All right. Anyway, maybe it was clear already. Good. So, I think I used to get confused by it. Anyway, all right. So we need to know the Hamiltonian. Blah blah blah. All right. So let's get back to the example we were doing of the scalar field. Basically, as I've told you, you already know quantum field theory. If you were stuck on a desert island, you would be able to reconstruct everything just knowing the rules of quantum mechanics with a bit of thought and application. So let's look at the scalar field. The scalar field. It's often called the Klein-Gordon field. So it obeys the Klein-Gordon equation. So if we just think classically for a moment, let's imagine there was a classical scalar field. A bit like the electromagnetic field, except it's a scalar, it's just one component, and it obeys a wave equation. It's just the standard wave equation with an extra term. Here, this term is interpreted as a mass. We'll see when we come to study the quantum excitations of this field, that m, this parameter m, plays the role of a mass. But for the moment, this is just a classical field equation. And the Hamiltonian is equal to the following. It's an integral over space of phi dot squared plus grad phi squared plus m squared phi squared. Now, I've just pulled that out of a hat. Let me just, you might want to just compare it with the Hamiltonian of the electromagnetic field, which is just the total energy. I integrate over an energy density, E squared plus B squared, with a factor of a half. If I work in the Coulomb gauge, if I write in terms of the vector potential, where E is minus A dot, so I've got the time derivative of the vector potential squared, and B is the curl of A squared. You see, well, okay, maybe this is plausible. There's a time derivative squared, and plus there's some derivative term squared. It's not all that different. How do we show that this is the Hamiltonian? Well, what we're going to do is later, we're going to find a Lagrangian L, which implies the Klein-Gordon equation. So CF, you're used to having a Lagrangian for a single particle, kinetic minus potential energy. That Lagrangian implies Newton's laws. What we're going to do later in the course is we're going to develop the Lagrangian field theory. We're going to find the Lagrangian which gives you the Klein-Gordon equation. And once you have a Lagrangian that gives you that equation, then you can work out the Hamiltonian. So we're going to show later on that this is the Hamiltonian. But for the moment, let's just take it that that's the Hamiltonian, because otherwise, to develop Lagrangian field theory, it is the same as the Lagrangian theory you're familiar with, but it's applied to a continuous field. It's just a bit more complicated. It's really the same thing, but a bit more complicated. Okay, so now what do we do? So we've got this classical theory. I have a classical field, obeys the Klein-Gordon equation. This is the Hamiltonian. We now need to quantize it. So to quantize the field, what are we going to do? We're going to let the field, at each point, classically, at time t, at each point in space, you've got a number. There's the value of the field. In quantum field theory, at time t, at each point in space, there's an operator. There's an operator that represents the field at that point. Similarly, the time derivative, the classical time derivative, just becomes the time derivative of the operator field. And this is going to turn out to be something important. The time derivative of the field, we call it pi, it's an operator, we call it pi. This turns out to be the canonical momentum density. Now we're going to see this again when you do the Lagrangian theory. You're used to defining a canonical momentum. Let me write it like this. Okay, you've seen, you've done basic Lagrangian theory. I have a Lagrangian, the partial derivative of the Lagrangian with respect to the time derivative of the coordinate defines the canonical momentum. Okay, in field theory, what we're going to have, in field theory, the analog is going to be this. Where pi, so this is the canonical momentum. Sorry, in particle theory, this is the canonical momentum, and this is the Lagrangian. In field theory, this pi is a canonical momentum density, and this calligraphic L is a Lagrangian density. So we'll develop the formal theory later, but let me just tell you now that it turns out when you look at the Lagrangian for the Klein-Gordon field, you look at the canonical momentum density, it turns out to be equal to the time derivative of the field. Okay. All right. So now what happens when we want to quantize the field is, you see what I'm doing, I'm giving you a sketchy overview of what the theory looks like. Rather than first develop, we're going to develop all the theory properly. Don't worry, we will. But if I did that first, it's going to be weeks and weeks to develop all this theory properly, and then finally you'll see, okay, now I see what the basic structure is. The basic structure, and then it's only then that you might begin to realize that, hang on, it is actually just ordinary quantum mechanics. I want to impress on you from the beginning that it's ordinary quantum mechanics. Anyway, you'll see the method in my madness eventually. Okay, so now the other thing we're going to impose are the canonical commutation relations, which we mentioned last time, writing in terms of the canonical momentum density. They look like this. The field operator, if I look at the commutation relation between between the field operator and the canonical momentum density at two different points in space. They obey this commutation relation, which is, as I emphasized last time, the same as your usual. Here's something that you're used to. If I have, say, a particle with position and momentum with different components, I, j, where I is 1, 2, or 3, then you're familiar with these canonical commutation relations. And these are the same because what we have is our field system if you make a discrete version, so imagine here is space, let me just draw space as two-dimensional. Instead of dealing with the field at every single point in space, let me just write down the field values at points on a lattice, where the lattice has a spacing epsilon. So at this point, there is some field phi I, and there is a canonical momentum density pi I. Let's just, instead of having the field having an argument x, let's just give it an index I, where I is a discrete index that labels its points. You are just applying standard quantum mechanics to the field. If you take this relation and you say, right, instead of having the position of a particle, x, what I have is, instead of having the position of a particle and quantizing it, I've got the value of a field at a given point, and I'm quantizing it. Okay? My degree of freedom, instead of my degree of freedom it being the position of a particle, my degree of freedom is the value of a field at a given point. So these particle positions correspond to field values. The canonical momentum Pj, what does it correspond to? Well, it corresponds to the canonical momentum density times little volume element, epsilon cubed. There's a little volume element around that point. Okay. So if I make that replacement, put that in here, so I just apply the same relation. What do I get? I get the following. That the field operator at the ith lattice point and the canonical momentum density at the jth lattice point satisfy the following commutation relation. I delta ij divided by epsilon cubed. Okay, I've just applied the same standard canonical commutation relation. And what happens in the continuum limit if I allow this epsilon lattice spacing to go to 0, if you think about it a bit, you'll realize that delta ij divided by epsilon cubed is just the same as the three-dimensional Dirac delta function. It plays the same role. We'll do all this properly later, okay? But just to give you a sense that when you apply, this might look a bit weird. What is this? This delta function? It's exactly the same. I've said this about 5 times or 6 times, or I say it one last time. It is exactly the same as the standard canonical commutation relation of so-called non-relativistic quantum mechanics. There's no difference. It's just you have, your degrees of freedom are now, at every point in space. So because you're applying it, instead of a discrete index, you have a continuous index, and you end up with a Kronecker delta becomes a delta function. Okay, So then what else? All right, so now, how to, we've got the canonical commutation relations. Let me just rub this out and just have those there. We've got the Hamiltonian. The Hamiltonian, to quantize, we've let these classical fields become operators. We've also let, the Hamiltonian becomes an operator. So in here, these terms are all replaced by their operator analogues. So I have the field operator, its time derivative, squared, plus the gradient of the field operator squared, plus m squared times the square of the field operator, integrated over all space. All right, so now we have everything. All right, this defines, let me say this loud and clear, this defines the quantum field theory of a free scalar field. You've got the Hamiltonian, you have field operators, you've got the canonical commutation relations. That's it. Everything follows. Everything follows from what we've written down. Well, using, of course, the Heisenberg equation of motion. Okay, so we're using, of course, the Heisenberg equation of motion. Everything follows. So, if you write down the Heisenberg equation of motion for the field, you can work out its first time derivative, and what you will find, in fact, that's something I've written slightly incorrect, well, not really incorrectly, but let's say more usefully, this phi dot is the canonical momentum density. So phi dot squared is best to write it as pi hat squared. Because pi hat, you're used to writing in ordinary quantum mechanics of a particle, you write the Hamiltonian in terms of position and momentum rather than position and velocity, using position momentum operators. In quantum field theory, when you write down the Hamiltonian, you write it in terms of the field operator and the canonical momentum density operator. Okay, so this is how you'd write it. And of course, you've got these commutation relations for phi and pi. So now, something we'll do a bit later in the course is, I think there's the homework problem where you have to work out this commutator. I wouldn't ask you to do it now because but in principle, if you instead of going out Saturday night wasting your time at Nick's, stay at home, see if you can work this out. See if you could work out the commutator of the field with the Hamiltonian, defined by this integral, using this. We'll be doing it later on, but you could do it now too. But you should find that it turns out to be just pi hat, and it's analogous to, you imagine if I had a Hamiltonian that's p hat squared over 2m plus b, and we looked at this last time, and I say, well, all right, what's the time derivative of the position operator? I've got to work out the commutator of the position operator with the Hamiltonian. And of course, I use the fact that x and p are equal to I, the commutator is equal to I, or I h bar. This turns out to be just p hat over m. Okay, simple. This is really basically exactly the same, except if you think of this integral, if you discretize this integral, it is actually just a sum over many points in space, where at each point in space I've got a momentum squared and something that depends on the configuration. It has the same form as this. There's a momentum squared, and here there's something that depends on x. It's actually the same thing. But anyway, we'll do this later in detail. If you work out this commutator, you get pi hat, and if you then work out the second time derivative of phi, well, what is this? This is the first time derivative of pi hat. And how do I work out that? Well, I use the Heisenberg equation of motion. So this is minus I pi hat h. So now what do we have to do? We have to work out the commutator of pi hat with h. Again, using, I hope I'm making myself clear that when you work out this commutator, or this commutator, you use this here. You use the canonical commutation relation, just as when you work out this commutator in ordinary quantum mechanics, you use this commutation relation. Okay, it's the same stuff. All right, what does it come out to be? It comes out to be del squared phi hat minus m squared phi hat. That's what it comes out to be. In other words, we get the Klein-Gordon equation, which is, of course, what we should have got, because we're supposed to have written down a Hamiltonian. So what we've shown is that, well, that what we have is consistent. Remember, we started with a classical theory. We said, here's the classical wave equation, here's the Hamiltonian that you get from the classical Lagrangian. Then we set up the quantum theory. Okay, now let's look at the Heisenberg equation of motion for the field operator. It does indeed, as you expect, turn out to be exactly the same as the classical field equation we started with, okay? Which is what usually happens in the Heisenberg picture. Just as, for instance, if you work out the second time derivative of the position operator, here you will get minus the gradient of the potential divided by the mass. Okay, just you get Newton's law. Here you get the classical wave equation. All right. So now what do we do? So let's see what we have. Let us write down what we have so far. What we have so far is we've quantized the system. So we have, these are now operators. This is an operator field equation. Our Hamiltonian is an operator. We're going to write phi dot as pi hat. And we have these canonical commutation relations. And we've already used the Heisenberg equation of motion. We've already used it, and it's given us this. So this is from the Heisenberg equation of motion. So this is where we are so far. So now what do we do? Now, and here's the convenience of working in the Heisenberg picture. You're familiar with the properties of classical wave equations. So you know that I could write the general solution Let's write the general solution as a linear combination of plane wave solutions. So basically, we've got the theory written down. It's now a question of, well, how do we analyze its physical content? So if we write this solution, we have our operator Klein-Gordon field, I'm going to write it, again, I'm just going to ignore there's an overall factor in front of the sum. I'm going to write it as a linear combination of plane wave solutions where I have some arbitrary coefficient, which is an operator. The coefficients, remember the coefficients, normally if I have a classical field and I expand it as a series of plane wave solutions, there will be some arbitrary coefficients, which are numbers. Here it's an operator field. So the arbitrary coefficients are actually operators. And I've written in this sort of slightly odd-looking form, if you've not met it before, slightly non-standard Fourier series, if you like. This form ensures that if I take the emission conjugate of the field, then basically the field is Hermitian. It ensures that the field is Hermitian. Because we started out, we're talking about what is called a real Klein-Gordon field, something which I don't think I mentioned, I should have mentioned at the beginning when we started with our classical Klein-Gordon field, with the classical Klein-Gordon equation. We're assuming that it's a real scalar field. Okay. Later on, we'll also do the complex scalar field. Things have become a bit more complicated, but for the moment we're doing the real Klein-Gordon scalar fields. I should have mentioned that. The real Klein-Gordon field. If classically I have a real Klein-Gordon field and I quantize it, then the operator is Hermitian. So I have a Hermitian operator field. Okay, it's a Hermitian operator. So imposing that it's Hermitian is a real, classically it's real, quantum mechanically it's Hermitian, so writing this form. All right, where the frequency omega is restricted to be mod k squared plus m squared. Why is it restricted to be that? Well, you know perfectly well, if I plug in, if I put that into if I want this to be a solution of the Klein-Gordon equation, then it doesn't take much to show that omega squared is mod k squared plus m squared. All right, for that to be a solution. So I'm just, you know, we're expanding it. It's writing the field as a linear combination of plane wave solutions of this partial differential equation. So omega has to be root mod k squared plus m squared. So now what we do is, once we have, so the nice thing about the real Klein-Gordon field is that it gives you an example of all the essential mechanisms of quantum field theory. All the other examples that we're going to do, the complex Klein-Gordon field, the electromagnetic field, the Dirac field, they're just more elaborate versions of the same thing. The electromagnetic field, you've got three components. It's a bit like having three Klein-Gordon fields, except well, there's a little bit of a twist. It's also, in the electromagnetic case, the mass is zero. There's no mass term. But the rest is similar. The Dirac field is you have a four-component field, and the wave equation looks a bit different, but it still has plane wave solutions. The basic structure is similar. Though there is a twist with the Dirac field that I'll mention a bit later again, but the twist with the Dirac field is that the commutators become anti-commutators. And it has to do with the fact that the Dirac field describes fermions, not bosons. We'll come to that. So there's a slight twist with the Dirac field. But apart from that, basically everything that I'm showing you here is a kind of blueprint for how quantum field theory works generally. Okay, so that's why I'm laboring this, going over it slowly. Because if you get this, then the rest is just the same, just a bit more complicated. More components, more indices. There's a funny anti-commutation for the Dirac field, but everything else goes through the same way. All right, so now we've written down our field expansion for the operator. What are these? These coefficients are arbitrary, unknown arbitrary operators. But there's something we haven't done yet. What we've written down, there's some information we haven't used. Okay, well, here we've written, so this equation, the Heisenberg equation of motion implies this field equation, which implies this expansion. Okay? But the quantum field theory is not just the Heisenberg equation of motion, it is also the canonical commutation relation. So we have to add in this here. So what we do is, from the field expansion, I can write phi hat, which is phi hat dot. What's phi hat dot? If I take the time derivative of this, let me just write, I mean, there's a factor in front that I'm not bothering to write in, but what am I going to get? If I take the time derivative, remember these coefficients here are just constant operators. The time derivative here brings down a minus I omega. I'll get a minus I omega, a k, e to the I, k dot x minus omega t. And here I will get a plus I omega, dagger. All right, I've got an expression for the canonical momentum density operator. And now what I have to do is I'm going to plug so I've got these two expressions. I've got an expression for the field as a sum over plane waves with these coefficients, and I've got an expression for the canonical momentum. People often get tired of saying canonical momentum density. You just call it the canonical momentum. And sometimes you get tired of even saying canonical momentum. You just say momentum. Okay, so you know what I mean. Okay, the canonical momentum, if you plug these two expressions into this thing, the canonical commutation relation, the CCR. Now, those of you who fancy, you think you're brave, you're feeling brave, you might want to do this, you might want to try this at home. See if you can show that if you plug those expressions into here, it follows that. These we'll do this probably later, but if you want to have a go at it now, have a go. It follows that these coefficients obey the following relation. K prime is delta K primed, and also AK. If I just look at the A's, not the A daggers, these commute. And if I just look at the A daggers, for different K's or for the same K, they commute. So basically, all of these coefficients commute with each other, except A and A dagger for the same K. If K is equal to K prime, this is 1. If K is not equal to K prime, this is 0. What you can then do is you can then plug in the same expressions into the Hamiltonian. And if I plug, so these expressions, I mean, I just dropped it out, but I have a series for pi hat. I've got a series, sorry, I have a series for phi hat, and I've got a series for pi hat. If I plug these two expressions into here, sorry, there's a squared missing. This should be pi hat squared. I don't know where that went to. So you take this series, you square it, and you integrate over all space. Okay? And similarly, you take the series I had for phi hat, you take its gradient, and you square it into it. Anyway, you work out these terms. You find if you plug these into this expression here, okay, you take those two series expansions for phi and for pi, you plug them into the Hamiltonian, you find that the Hamiltonian is equal to the sum over k of h bar omega, a hat dagger k, a hat k plus a half. Are there any questions about this so far? Any questions? So if you feel you're not sure, you could work this out all out on your own. Don't worry, because we're going to do it all properly later, okay? But just to get the structure. So, what has happened now? We have ended up, at the end of the day, we're quantized. Let me just rub all this out and just write down what the end results are. We quantized the real Klein-Gordon field. And what are the results? Results for quantization of the real Klein-Gordon field. The results are that the field phi can be decomposed into plane wave modes labeled by a wave vector k, and a frequency omega, which is the square root of log k squared plus m squared. Plane wave modes. The system okay, the total Hamiltonian, H may be written as H hat. It's a sum over wave vectors times H bar omega, A hat dagger K, A hat K plus a half, where A hat K, A hat dagger K are constant, in other words, time independent operators satisfying commutation relations. So what I'm writing down for you here is everything that comes out. When you quantize the the real Klein-Gordon field, the result is simply this. Okay, this is the result. That the field operator can be decomposed into modes labeled by a wave vector k and a frequency omega that's given in terms of k. The total Hamiltonian for the system can be written as a sum like this, where these quantities are just constant operators satisfying these commutation relations. Right? This is the upshot, this is the end result of what we have done so far. Okay, so what does this mean? Conclusion. What does this mean? Conclusion. So mathematically, the field system is equivalent to a collection of independent simple harmonic oscillators. So, with you have one simple harmonic oscillator for each mode, i.e. for each wave vector k. This summarizes, so just mathematically. Now this is not to say that, oh, there are all these, masses on springs running around in space. What we're saying is that you have a field system, you quantize it, mathematically the result is just like saying, well, I have a sum over modes. For each mode, I could define h hat k to be, this is the Hamiltonian for the kth mode. So I can write h hat is a sum over k, h hat k. So this is the Hamiltonian for the mode k. And the Hamiltonian takes exactly the same form, if you remember from your basic quantum mechanics, when you quantize a harmonic oscillator. It takes exactly the same. This is what you get when you quantize a harmonic oscillator. Instead of x's and p's, you introduce these operators a and a dagger. The Hamiltonian for a simple harmonic oscillator looks exactly like this, where these quantities obey, if I have one mode, I have h hat k is h bar omega a hat dagger k, a hat dagger plus a half, and I have, if I'm just looking at one mode, then the relevant equation is the commutator of a hat k with a hat dagger of k. Okay, so putting k prime equal to k, this is just one. So one mode, this is what you get for each mode. It's just your usual simple harmonic oscillator. And I've got lots of them. So now, what does this mean? So, just look at one mode for the moment. Let's just look at one mode. And each mode, if I just look at one mode, so each mode, you know, we don't have to go over the theory of a simple harmonic oscillator again. You know that from this Hamiltonian and this commutation relation, you can show that there is an evenly spaced set of energy levels, something you do in basic quantum mechanics, for the harmonic oscillator. So each mode has energy levels. So I'm going to keep the label K, because we're talking about the kth mode, but let's just think about just one mode for the moment. Each mode, let's label it K, each mode K has the following energy levels. Nk plus a half, where Nk is an integer, which can be 0, 1, 2. Okay, that follows from this. If I have this, if I say this is my Hamiltonian, so I'm looking at the eigenvalue problem. I want to find the energy levels for this Hamiltonian. If you use these commutation relations, and you're clever, or if you're not so clever, just look it up in your old quantum mechanics textbook, you'll find the derivation that these energy levels from this commutation relation, you show that you have these energy levels, evenly spaced energy levels. So we can draw a little picture. We've got a single mode labeled by wave vector k, and we have evenly spaced energy levels. So here we've got Nk is 0, Nk is 1, Nk is 2, Nk is 3, going on and on. What is this? If I look at the ground state, when Nk is 0, the energy is just a half. So I put in h bar. In this course, really, h bar is 1, but sometimes I put in h bar just to give, because you're used to seeing, it might look a bit odd seeing it without the h bar. So now again, I'll just put in the h bar. This is the ground state, the familiar ground state of a simple harmonic oscillator system. When Nk is 1, the energy is a half h bar omega, the ground state energy, plus h bar omega. So I have one excitation. Instead of being in the ground state, I'm at the excited. The mode is excited, is at the first energy level. When Nk is 2, I have a half h bar omega plus 2 h bar omega. So I have 2 excitations in the second excited state. Let's just do one more. The third excited state. 3 excitations, the third excited state, and so on. These are the energy levels of a single mode of a quantized scalar field. Now, let me just tell you now the key point in the interpretation of this. So, let us say I have, okay. First of all, remember I haven't just got one mode, but an infinite number of modes. Many modes. So I've got So the mode labeled K has a discrete set of energy levels. The mode labeled K prime also has a discrete set of energy levels. And there are an infinite number of such modes. Okay? The infinite number of wave vectors. Each wave vector has its own set of evenly spaced energy levels with a Hamiltonian that looks like this. Let us take the case where nk is equal to 1, and all the other nk primes are equal to 0. So what do I mean? I mean that, well, the K mode is in the first excited state, whereas all the other modes are in the ground state. Okay, let's imagine that. Just one of the modes is excited. All of the other modes are in the ground state. What we can show, this corresponds to a quantum state psi such that the total, if you let the total Hamiltonian act on the state, you find an energy a half h bar omega plus h bar omega psi, where omega corresponds to the wave vector k. And there's something called the total momentum, which we'll look at later. So that you know that the Hamiltonian operator is the total energy operator. You can define something called the total momentum operator. And you can show that when it acts on this state, it's an eigenstate with eigenvalue h bar k. So this state is an eigenstate of energy. This state here is an eigenstate of total energy. A half h bar omega plus h bar omega. It is also an eigenstate of total momentum. Momentum h bar k. Now, the interpretation of this, interpretation. So first of all, I'll put this in parentheses, is you take the, I'll talk about this more later, but you take the ground state energy, a half h bar omega. Sorry, I've made a slight mistake. Hang on, I made a slight mistake. This is not quite right. I should have said this before. I wanted to skip this. Sorry, let me just backtrack slightly. Be aware. If I have the ground state for all modes, so all the modes are in the ground state. All the modes are in the ground state. The total energy is a half h bar omega plus a half h bar omega prime plus, in other words, is equal to a sum of a half h bar omega over all the modes. Okay, if every single mode is in the ground state, so this is what we usually call the vacuum. It's usually what you call the vacuum. None of the modes are excited. I should have done this first, but I wanted to skip ahead. Anyway, imagine none of the modes are excited. Every mode is in the ground state. Well, there's still an energy. Each mode has an energy. So empty space, or the ground, the lowest energy state, is equal to this, which is actually infinite. This thing actually diverges. It's called the divergent vacuum energy. And it is a problem. It is a problem in quantum field theory. Some people solve it by assuming there's some high frequency cutoff, or there's some maximum that the frequencies cannot be. If you convert this into an integral over omega, it diverges when omega goes to infinity. Some people think, well, maybe there's a maximum frequency that can be allowed. But there's there's a trick to avoid this, is you just subtract from this quantity from all energies. In other words, you take this as the origin. So it's like saying, well, if I have my energy scale, I'm going to start with the ground state and then just consider energies above the ground state. This ground state is actually infinite, but I'm going to subtract that infinite constant. So what that means is that this term here, this doesn't appear. This a half h bar omega doesn't appear here. I just have, if I have a situation where if these were all in the ground state, I've got the infinite vacuum energy. If I have one mode excited, I have the infinite vacuum energy plus h bar omega. Okay, so I've got a single h bar omega energy on top of the vacuum, or on top of the ground state. And this is a bit of a, this is a trick. It is a problem actually in quantum field theory, but this is a bit of a cheap trick. It's a cheap trick, but this is the state of theoretical physics. There you go. The vacuum formally has an infinite divergent energy. When the vacuum is excited, you get some small finite excitation on top of the vacuum. They're the energies we consider. We just take the vacuum energy as our zero, if you like. Okay, so coming back to this, what is the interpretation? So the interpretation of this is that, well, it's the ground state, it's the vacuum state, there's no excitation, the lowest possible energy state of this field system in space. If I have one mode excited, it is an eigenstate of total energy, if we measure relative to the vacuum, so of total energy h bar omega. Let me maybe put here. Relative to the vacuum, or ground state. Okay, if I measure relative to the vacuum or ground state, the energy of this state is h bar omega, and the momentum is h bar k. This state is an eigenstate of the energy operator and the momentum operator. The interpretation, I'm just going to write one last thing here, and I'll let you go. The interpretation of this state is the state sign. In other words, this state here, where there's just one mode excited, corresponds to the presence of one particle, I'll put this in quotation marks, one particle with energy h bar omega and momentum h bar k. Now we're going to discuss this a lot more on Thursday, but something to take home and think about it. I have my field system corresponds to an infinite number of harmonic oscillator systems. If they're all in the ground state, that is what we call empty space. There's nothing there, except actually the energy turns out to be infinite, but we ignore that problem. We imagine we'll take that as our zero of energy. If now one of the modes is excited in the first energy level, the total state has an energy h bar omega and a momentum h bar k, and we interpret this as corresponding to the presence of one particle with energy h bar omega and momentum h bar k. So what happens in quantum field theory is that what you normally think of as particles, they are in fact excitations of field modes. And what we've done here, we have one mode excited, we've got one particle. If you have many modes excited, you have many particles. We'll talk about that more on Thursday. Any questions? All right, so we'll continue on Thursday. Thank you.